Good morning, students. Mr. Carver here. Today we're going to be doing section 2.2, that is basic derivative rules. I'd like you to start out, though, with this warm-up. Before we get going here, I'd like you to tell me if this function is differentiable at x equals positive 1. I'd like to prove differentiation. So you can pause this. You can work on this right now. So again, first of all, once you're ready to go, hit play. I'm going to go ahead and work it now. First of all, you need to show continuity at x equals 1. And I think we can go through that. So I've got f of 1 is equal to 0. That is the fifth root of 0. So check. Step 2, if I take the limit as x approaches 1 of f of x. This is not a piecewise function, and I can check that limit just by plugging in 1, and I do get 0, which is a good sign because f of 1 equals the limit as x approaches 1 of f of x. So not only do we have a dot and the two sides coming together, but the dot and the point where they come together are in fact the same y value. So this is continuous. Now remember, a function may be continuous, but it may not be differentiable. So if a function is not differentiable at a given value of x, it is either discontinuous at that value of x, or there is a sharp turn in the graph or a vertical tangent line. So that's the next step. We need to check that since we have continuity out of the way. All right, now to prove differentiability once we have continuity proved, we're going to go through this process, and this process actually has a name. It is called the alternate form of a derivative. The alternate form of a derivative is the way to prove differentiability once you have established continuity. And if you recall, it is nothing more than the slope formula. So what we're going to do is we're going to take the limit as x approaches 1 from the right-hand side of f of x, which is x minus 1 to the 1/5 power, minus f of 1. We already know that's 0 from our continuity proof, all over x minus 1. And incidentally, we're going to show this from both sides. So again, it's f of x minus f of c all over x minus c, and our c value in this case is 1. You'll notice in both of these cases, when you plug in 1, either from the left or from the right, you do get 0 over 0, which means we need to do something to this. Now, I do have a root, and I have a difference, but one of the terms is 0, so multiplying by the conjugate is not going to actually help us here. What I'm going to do is reduce. I've got 1/5 power on top, and I've got 5/5 power on the top. So this is going to reduce to 1 over x minus 1 to the 4/5 power in both of these. And what you'll notice is that both of these reduce to this. So now what I've got is 1 over 0. 1 over 0 indicates a vertical asymptote, and as you recall, if I'm approaching a vertical asymptote from one side or the other, I'm going to get either positive or negative infinity. If I come in from the right-hand side, this is 1 over a very, very, very small positive number taken to the 4/5 power. So fifth root gives me positive, fourth power gives me positive as well. This is going to go to positive infinity. Now when I come in from the other side, this gives me a very, very, very small negative number. Taken to the fifth root is continued to be negative. Fourth power makes it positive. This also goes to positive infinity. So what I have here is non-differentiability. But to describe the non-differentiability, I would say that this is a vertical tangent line. And to give you a quick sketch, what I have here at positive 1 is something that looks like that. I've got positive infinity slope coming in from the left and positive infinity slope coming in from the right. So it is not differentiable. And the alternate form of a derivative shows, with the two-sided limit, that it is in fact a vertical tangent line. All right, so let's get into 2.2, basic differentiation rules. In 2.1, what we did was we found the derivative by using the limit process, forcing delta x going to 0. Now we're going to actually just dive into some rules here. I'm going to give you the rule title. You don't need to remember the rule title. I just want you to be able to know how to apply the rules. All right, so we'll start off with the most basic one, and it is actually the constant rule. And here it is. When you derive with respect to x, and by the way, this is a command, and this tells you to derive what follows in terms of x. And we'll get into a more thorough investigation of what that actually means in terms of x as time passes. But for right now, what we're doing is we're just deriving the following expression, and we'll just make this c, which is just a constant. Now remember, this is the function that we are deriving here, so it is y equals c, and if c is just a constant, you just have a horizontal line at some y value c. It comes through there like that, and as you can see, no matter where you're at on that line, the slope of that line is always 0. So when deriving a constant, you always get 0. All right, the next rule is used very frequently. It is called the power rule. I think my pen needs to be charged. The power rule. And it says something like this. If you have f of x, if you have some f of x, and this is x to the... All right, let me try this again. Press a little harder with the pen. This is the power rule, which is the next. If you have, say, f of x, rather, is equal to x to the n, where n is just a constant. You may have noticed this as you've gone through the derivative process. What you get then is f prime of x, a derivative of n times x to the n minus 1. So essentially what happens is this exponent goes down to the front, and then you take 1 away from the exponent, which leaves you one less powerful exponent. And that was noted by a few of you in class. For instance, if you had something like this, and f of x being something like a third degree, what you ended up with is a derivative that was, in fact, a second degree. And that's what you're seeing here. A third degree polynomial will be knocked down to a second degree polynomial. Right, let's get rid of this. And we'll work through a couple of examples. So for instance, let's say you have something like this. Let's say you've got y is equal to the square root of x, which we know is x to the 1/2 power, right? First power, second root. When I derive this, I get a y prime of the 1/2 comes down to the front, and I take 1 away from the exponent, which gives me negative 1/2. I'd like you to write your answers with a positive exponent, so that x to the negative 1/2 moves to the denominator. So that is 1 over 2 x to the 1/2, also known as 1 over 2 root x. So that is your derivative. All right, now let's say you've got something like y is equal to 3x squared. When you derive that, the exponent comes down to the front, giving you 3 times 2. When that exponent moves down to the front, you multiply by whatever constant is there, and then I take 1 away from the exponent. That's a 1. So this gives me 6x to the first as my derivative. And again, that is the slope machine for that curve right there. So if I want the slope, say, at x equals 3, my slope would in fact be 18. All right, the next rule is the constant multiple rule. Hopefully you guys can read my handwriting. Constant multiple rule basically says this: if you take the derivative with respect to x of a constant times some function, let's say it's f of x, what I end up with is the constant times the derivative of the function. And that's actually what you've already seen. The example that I did here mere moments ago was y is equal to 3x squared. 3 then being your constant. When you derive that, you get y prime is equal to, that's a y prime there, 3 times the derivative of x squared, which is 2x to the first, using my power rule. And then you just multiply the numbers out front. So I get 6x to the first. So the constant multiple rule just allows you to keep constants out to the front and multiply the derivative of the variable by it. Let's do another quick example. Let's say I've got y is equal to 7x to the 2/3 power. I've got then 7 times the derivative of x to the 2/3, which is going to be 2/3 x to the negative 1/3. And then I just multiply the constants out front. That is 14/3. And I'm going to move that x to the bottom. That is x to the 1/3, also known as 14 on the top. 3 times the cube root of x on the bottom. I would take either one of those two forms. So suddenly, deriving has become much, much more easy than it was before using the limit process. So that's exactly what this process or what this section is all about. All right, just a couple more here. Let's do the sum difference rule. And the sum and difference rule allows us just to derive sums and differences independently. So here's the way the notation reads. It's the derivative with respect to x of f of x plus or minus g of x. Then you just do them separately. That will give you f prime of x, the derivative of f, plus or minus the derivative of g. And again, you just go through and just derive them each individually using whatever rule you need to use. So for instance, let's say y is equal to 3x squared plus 4x minus 2. When I go to derive that, I just do them each separately. So this first term here, 3x squared, is going to derive to 6x to the first. The second term there, the 4x, will derive to 4x to the 0 power, and x to the 0 power is just 1, so I get 6x plus 4. And then, of course, the last term here, negative 2, goes to 0. So my derivative is 6x plus 4. All right, now, before I move on to the last two, please put this rule in your notes. Do not derive the following: products, quotients, or quantities other than just x which are raised to a power. And I'll just put the caveat, yet. I'm going to teach you how to do all these. For all of these, I would like you to rewrite before deriving. And when I say rewrite, I really mean simplify before deriving, which is going to then remove products, quotients, and quantities other than x raised to a power. So let me give you an example of what I mean. Let's just say I'm deriving y is equal to 1 over 2x to the 5/4 power. one thing you'll notice here is that I have a quotient. I have 1 divided by 2x to the 5/4. So what I want to do is rewrite it so that I get rid of the quotient. Now, I'd like you to think of it this way. This is the same as 1/2 times 1 over x to the 5/4. And that is because 1/2 does not impact this process. The 1/2 is just a constant out front. It's just going to stay out front according to the constant multiple rule. So what I'm going to do is rewrite or simplify this. Now, when I say rewrite, what I'm talking about is eliminating the quotient. And in doing that, in order to do that, rather, what I will do is take that denominator and I will move it to the top, which is going to give me y is equal to 1/2 times x to the negative 5/4 power. Now, technically, that is still a quotient, but it's not written in quotient form. Also, you may be thinking that you have a product here, which is on my prohibited list. The product is only a problem when you are multiplying two variables. 1/2 is a constant, so I don't need to worry about it. So that's exempt from the product prohibition. So now when I go to derive this, I've got y prime is equal to 1/2 out to the front, and then I just derive this section just like normal. I bring the exponent down to the front, and I take 1 away from the exponent. And then, of course, I just clean this up with positive exponents. So I get a -5 on the top. I have 8x to the 9/4 in the denominator, and that is my derivative. Let's take a look at another example. Let's say I've got y is equal to 3x plus 2, and I'm going to square it. And I've got a couple of problems here. This actually violates 2 of the prohibited operations. One is a quantity other than just x raised to a power. 3x plus 2 is more than just x. I also have a prohibition of products. And I think you would agree that 3x plus 2, the quantity squared, is the same as 3x plus 2 times itself. Either way, I have a problem. So I need to get rid of this product or get rid of the quantity raised to a power by FOILing it out. So now I have y is equal to 9x squared plus 12x plus 4. And now I can just do them each separately, and I just have products of a constant with a variable, and just a constant. So I can go ahead and derive this. My y prime is equal to 18x to the first plus 12x to the 0 plus 0, and that is my derivative. All right, the last two things I'd like to show you. First of all, what I'd like you to do is I'd like you to sketch the sine curve. You can pause this and sketch it yourself. And I'll sketch it. So it's a period and change of the sine curve. And I'd like for you to sketch the sine derivative just going from here over to there. Let's just do one period of the sine curve. And again, you can pause this and try it on your own, because I'm going to do it right now. All right, remember when you're sketching the derivative, I'm going to first put in 0 slopes, which are there and there. And then I'm going to start at the y-axis. It looks like I have a slope of about 1 going to 0. In between that dot and this dot here, it looks like my slope will go from 0 to negative back to 0. So maybe something that looks something like that. And then as I go back over to that red mark there on the x-axis, it looks like my slope goes from 0 up to positive 1 again. And I think that you can see that y prime, or the derivative of sine of x, is in fact the cosine of x. And I'm going to have you memorize this. Let's see if it works the other way. So what I'd like you to do now is graph one period of the cosine of x. And you can pause that while I do it here. I'll just do one period of the cosine. And I'm going to sketch the derivative now. So the derivative, I'm going to put in my zeros. And I'm going to start off at the y-axis. It looks like I go from 0 to negative back to 0. So it looks something like this. And then going from this dot to this dot, looks like the slope goes from 0 up to positive 1 back to 0. So in fact, it doesn't quite work the other way, but my y prime, or the derivative of the cosine of x, turns out to be the negative sine of x, or the sine of x reflected over the x-axis. I'd like you to memorize that as well. All right, so if I have y is equal to 4 times the sine of theta plus 2 times the cosine of theta, and I go to derive this, I'm just going to use my identities that we just learned. Sine goes to cosine, so I've got 4 times the cosine of theta. Cosine goes to negative sine, so actually we can make that a minus 2 sine of theta, and this is the derivative, or the slope machine, of my original y. All right, students, thanks for watching. That should be enough to get you through today and tomorrow, and I hope to see you guys soon. Take care.